Hello everyone, today we'll talk about the problem find valid matrix given row and column sums. A self-explanatory title for a very natural problem. We want to get a matrix of non-negative integers, but what we're given is just the sum of values in every row and the sum of values in every column. So we have to reconstruct that matrix. We're also given a guarantee that indeed there is at least one matrix that satisfies the requirements. So you might imagine that they had some matrix, they calculated those sums, and then they gave those sums to us. And we have to reconstruct any matrix for which those sums will be the same. So, how do we approach a problem like this? The first thing that we can notice is that we want our matrix of some height and some width to be h times w in size. So consisting of h times w numbers, where h and w are respectively the length of this array of row sums and of column sums, which means that we're given fewer numbers, way fewer numbers, because only a linear amount of numbers, corresponding to the much bigger set of numbers that we have to generate, because we have to generate a quadratic set of numbers, right? Which suggests to us that, of course, through the pigeonhole principle, but probably also generally, there are many matrices that will satisfy the row sum and column sum, which means that perhaps there are some easy matrices to conceptualize, to come up with, or maybe we can, for instance, assume that most of the values can be zero in the final matrix, only some values non-zero, and try to now focus which values have to be non-zero and what those values should be. So that's one way of doing it. And another way of doing it is that since there are so many numbers, so many matrices should correspond in general to a given set of row and column sums, then maybe it doesn't really matter what we do. Maybe we can just in every step do something that makes a little bit of sense. And finally, at the end, we'll get a correct solution. And both of those ideas are good, I think. One more thing that we should also note is that we're guaranteed that those row sums and column sums are valid. But what does it mean that they're valid? You can think about that, even though we have this guarantee. How do they look? What can we say about them? And of course we know that the sum over all row sums is equal to just the sum over the whole matrix. So it has to be equal to the sum over all column sums. So in other words, the sum of both of those arrays has to be the same. If it's not, then clearly that would be impossible to reconstruct that matrix. But maybe we can look at this fact and try to come up with a solution based on that fact. And at this point, we might already try to implement a solution and see if it works. One idea which we can do is to just select any position. Remember that our values have to be non-negative. So select any position where the row and column sum in that row and column are not zero, and increase the value in that position by 1, or maybe even by more than 1 if possible, and keep doing that and hope that it leads to a correct solution. And I think that it will lead to a correct solution, so that is one way to do it. A little bit more of a structured way would be to try to create values on the diagonal of our matrix. Not really, they have to stick on the diagonal, but we'll start at the upper left corner and go right and down. So that would mean that we put here something, and then we put something either here or here, and again either here or here, and we only go down and to the right. And of course going down and to the right has this nice property that we'll be doing steps down at most height minus 1 times until we reach the last row, and the same for width minus 1 steps to the right. So we know that we won't look at too many numbers, and if that leads us to a solution, then we're happy. That led us to a solution. And indeed this is the solution that I have implemented here. Another way of looking at the same solution would be to, for instance, get the matrix and first write all the row sums as the first column. So now the row sums are correct, but the column sums are not correct because everything is in the first column. And now we just push values to the right, and maybe the last value that we push will be pushed only in part. So for instance, if all those values are 2's, and we want this column to have a sum of 3, then we'll keep 1, 2, and one single 1, and half of that will be pushed to the next column. And then again we have rows are correct because we only push within a row. Columns maybe are not correct, we push them to the right. And we also hope that this will lead to a solution, and I think that it will indeed lead to a solution. So for specifics on this solution, we'll see the code, and later I'll tell you also how you can think about convincing yourself about the correctness of this approach. So we want to essentially go along the diagonal or go to the right and down appropriately. So we start at 0.00. And for as long as we're pointing at some position in our matrix, we'll do the following thing. We'll make sure that we're in a position where the row and column sum is not equal to 0. So we move the row forward and the column forward, respectively, when the sum is equal to 0. That's because if the sum that we currently need, because we'll be modifying the row sum and column sum arrays, if the sum is already 0, we cannot put anything in that row or column, because then it's impossible to have a sum being equal to 0 and add something that's non-negative, and it's not 0 because 0 is the default value. So we know that we cannot put anything there. Otherwise, we know that row sum and column sum are both positive, so we'll just put the minimum of those on our current position. And then we remember that this row and column now received a decrease by v, because already that minimum, that v, is accounted for by this value. And when we do it that way, by taking the minimum of those two values and subtracting it from both of those values, we make sure that at least one of those values becomes 0. So the total number of steps here is at most, well, number of rows plus number of columns. And also we go only to the right and down, so that is essentially the same idea that we had before. Because we know here that the number of steps is the first step plus h-1 plus w-1. And that also leads us to a pretty interesting thing, because here the number of steps then is w plus h minus 1. Here we can make w plus h steps, so maybe one more step. But again, that final step, is it possible to at the end have all the row sums be equal to 0, but some col sum to not be equal to 0, or the other way around? And of course it's not possible. In that case, it's not possible to create that matrix. And that leads us to the idea for a proof of correctness. And that proof of correctness, or at least the idea of thinking about the correctness of this algorithm, is a simple inductive argument. Because we can claim that this thing, this sum over row sums being equal to sum over col sums, which is trivially necessary, is also sufficient for those two arrays to be correct. And we'll look at it inductively. And that induction, as suggested by our algorithm, is to just look at the height and width of the matrix. So if we start at the matrix that's 1 by 1, then clearly those sums being equal means that they are a single value, and that value is the value in our matrix. And now, if we have a matrix that's m by n, if we reduce one of those two dimensions, one that's not equal to 1, because we cannot do anything other than that, then for as long as we make sure that all the row sums, all the column sums are still equal, and they will be, because by adding something at position of some row or column, we decrease both of those sums by the same thing, and we get a matrix that's smaller. Right, so essentially here we know that, and this corresponds to the fact that by taking this v and subtracting it, either one of the row sums or column sums becomes 0, and this would be the uppermost non-zero row, or the leftmost non-zero column. So we can imagine that by putting this value here, we either get rid of the first row, because now the sum becomes 0, or get rid of the first column. And after getting rid of it, we get a smaller matrix, and that matrix still has row sums being equal to col sums. And at the end, we finally reach a 1 by 1 matrix, and that 1 by 1 matrix is trivially satisfiable.